So the histogram that's involved with this, which is a good way to sort of displaying the shape of the distribution here. So you have a graph that appears to be roughly symmetric with this. So as far as interpretations go, if we're looking at how to interpret the following, what we would say is that the probability that x is greater than or equal to 1 equals 7/8. This means that if we were to repeatedly flip, and key emphasis here being on repeatedly, if we were to repeatedly flip 3 coins and record the number of heads, then in the long run, about 87.5% of the time, we will get one or more heads there. So that's just the interpretation of that right there. So in terms of the two different types of random variables, there are what are called discrete random variables. There are also what are called continuous random variables. And if we can find a way to list all possible outcomes for a random variable and assign probabilities to each one, what we have is a discrete random variable for something like that. So some examples of discrete random variables or some characteristics of discrete random variables. Every probability must be a number between 0 and 1, similar to what we said before. The sum of the probabilities must equal 1, and those are just the rules that we went over from probability models previously. To find the probability of any event, you would add the probabilities of that particular value that make up the event. So some different things involving discrete random variables. Even though a discrete random variable takes a fixed set of possible values, and you'll see this more clearly in the example, the set of possible values can be infinite. For example, if x were to equal the number of rolls a fair die needed to get a 6, there is no upper limit for x, meaning you could theoretically roll a fair die an infinite amount of times if you were going to do it until you got a 6. So example here, and here's the probability model that we have at the bottom, and the question says, in 1952, Dr. Virginia Apgar suggested 5 criteria for measuring a baby's health at birth: skin color, heart rate, muscle tone, breathing, and response when stimulated. She developed a 0-1-2 scale to rate the newborn on each of the 5 criteria. A baby's Apgar score is the sum of the ratings on each of the 5 scales, which gives a whole number value from 0 to 10. Apgar scores are still used today to evaluate the health of newborns. What Apgar scores are typical? Sort of what are typical here? To find out, researchers recorded the Apgar scores of over 2 million newborn babies in a single year. Imagine selecting one of these newborns at random. That's our chance process in this case. To find the random variable x equals Apgar score of a randomly selected baby 1 minute after birth, the table below gives the probability distribution for x. So just notice that it gives you all the possibilities here from 0 through 10. That's all the possible scores. And then this was the probability that a baby that they chose from the, what was it up here? They had 2 million newborn babies. The 2 million newborns. This was the probability that they had that score based on their sample of 2 million. So kind of moving forward here, part A says show that the probability distribution for x is legitimate. So it's legitimate as long as all of the possibilities are listed, which all the scores are listed here from 0 to 10. And if you add up all the probabilities, the total sum equals 1, and each of the individual probabilities is a number between 0 and 1. So those are the 3 things that need to be true in order for the probability distribution to be quote-unquote legitimate. Here's a histogram of the distribution of scores. You can see here from the histogram that it appears to be skewed left. The tail kind of moves to the left. The higher bars are on the right side over here. And then for part C, Apgar scores of 7 or higher indicate a healthy baby. What is the probability that x is greater than or equal to 7? So that's these 3 categories here, 7, 8, 9, 10. So the probability that someone has a score that's greater than or equal to 7 is 0.908. So we would say there that we'd have a 91% chance of randomly choosing a healthy baby. That's what they're considering to be a healthy baby, is a baby that has a score of 7 or more. So the questions here, I'll give you a few minutes to try this on your own, and it says North Carolina State University posts the grade distributions for its online courses. Students in Statistics 101 in a recent semester received 26% A's, 42% B's, 20% C's, 10% D's, and 2% F's. Choose a Statistics 101 student at random. The student's grade on a 4-point scale, A being a 4, is a discrete random variable x with this probability distribution. So here's the table of values that represents the probability distribution. So take a few minutes and see what you can do with those 3 questions on your own. So for question number 1, say in words what the meaning of the probability x is greater than or equal to 3 is. So what we would say there is that the probability that x is greater than or equal to 3 would mean the probability that the student gets either an A or a B is 0.68. So we get that simply from just taking these probabilities here and just adding those together, 0.42 and 0.26. For question number 2, write the event the student got a grade worse than a C in terms of values of the random variable x. That would be the probability that x is less than 2, which would be 0.12. You could also actually say here that the probability that a student, probability of x is less than or equal to 1 would also be an acceptable way to write that as well. And then for number 3, sketch the graph of the probability distribution. So here's the graph of that, and you can see from this that it's skewed left, which basically means the higher grades are more likely. You're more likely to get a grade that's, in this case, a B or an A, where there's fewer lower grades on the left-hand side here. So that's essentially kind of brings into, at least here in the beginning, what a discrete random variable is. One of the things that we will look at moving forward is some different things with what's called expected value, which is also known as the mean of a discrete random variable, and we'll also look at some different things with what's called a continuous random variable.